All right, we're going to have a quick little lesson here on 7.1. Integral is net change, and we're going to talk about how it relates to motion. So we're going to start out just with going over some of the important formulas, and you might have gotten them in class. Otherwise, you can add these to your notes. So the first thing is just this idea that we've been talking about really for the last couple chapters, that if you want to integrate a function f of x dx from a to b, then the formula for that, if you have an antiderivative capital F of f, you just plug in the top function value and subtract the bottom function value. Okay, so you do capital F of b minus capital F of a. This is especially useful if you integrate from t1 to t2 of v of t dt. Well, the antiderivative for velocity is just the position function. So that would be s of t2 minus s of t1. If we're thinking about position, velocity, and acceleration as kind of our tower of functions. To go up, you derive, and to go down, you integrate. So we aren't using acceleration really at all today, just really the velocity and position functions. But integrating our velocity function, we can figure that out by just taking the difference in positions. So then the most important formula that we learned today is if you want to know the position then at t2, all you do is you take the position at t1. So all I'm really doing here is adding s of t1 to both sides, and you add to it the integral from t1 to t2 of v of t dt. Now this works if you're going forwards or backwards. Often this is the initial position. It'll tell you where the position is at time 0, and then you've got to integrate from 0 to whatever time you want the velocity function to find your position at the new place. So what this integral does right here is it gives you displacement. So that tells you how much your position changes, which makes sense because it tells you the difference between the starting position and the final position. And then when we add all together, that gives me the final position. And the other thing we talked about today was the total distance traveled. So total distance traveled, there are a couple ways. If you're doing it by hand, then what you have to do is find the area of all the regions. So you add all regions. Because, for example, if you had something like this maybe. So this guy would be, if you integrate it, would be negative. This guy would be positive. What you have to do is actually add them together. So let's say the area of this guy down here was 1, and this is also 1. The total distance traveled would be 2, but it actually would have gone negative and positive the same distance. Its displacement would actually be 0. If it's with a calculator, you're just going to integrate from t1 to t2 the absolute value of the velocity function. Now it's important you don't take the absolute value of the entire integral, because what that would do is just find your displacement and then make sure it's positive. This is going to make sure that the function, like this, would flip this part up to the top. And then when you integrate that, it would give you an area of positive 2. Okay, so these are kind of the important formulas that we're going to use today, and this is true for any rate. It doesn't necessarily have to be a position and velocity function. Any antiderivative this will work for. So let's take a look at the worksheet that you guys have. So the first one, this is a calculator problem, in case you didn't know. And let's see what's going on. So first of all, they ask, so let's see, a particle moves along the x-axis, so its velocity can be modeled by this function between 0 and 5. The particle's position at 0 is 9, so s of 0 is equal to 9 is what they're telling us there. And they ask first, when does the particle stop? Well, a particle stops when the velocity is 0, so we need v of t to be equal to 0. So what you're going to do is you're going to probably solve this using the solve function on your calculator. What I did, though, is I actually made a graph of this function. So if you don't have a CAS, that is what you would probably want to do. So if you graph this function, what you get is that at 0, it's at -8, which makes sense. And then it kind of passes up through here like this. And then at 5, it's somewhere up there. So between 0 and 5, this is kind of what the function looks like. So the particle will stop when the velocity is 0. So that's that point right there. I have to figure out what that t value is. So if you have a calculator, you can graph it and use menu or analyze function, find the 0. The other option is you can use the solve function. So you just do solve and then type in your v of t function, or you could define it if you do v of t colon equals next to the 9. Remember, that's control and the button next to the 9, and type this guy in. You could just do solve v of t equals 0 comma t. And the answer I got for that, there was a negative option, but the only one between 0 and 5 was when t is equal to 1.2545. Make sure you have at least 3 decimal places, but that's plenty. Now that's when it's moving to the right. Well, a particle is moving to the right when its velocity is positive. So we need it to be positive. So it looks like if we look at our graph over here, since this is v, the velocity is positive after 1.2545. So that's going to be true from 1.2545 up until 5, interval notation there. Then it's moving left when the velocity is less than 0. That happens between 0 and 1.2545. Now they ask for the displacement of the particle. So if we just go back to our formula for that, that'll just be the integral from 0 to 5 of v of t dt. And again, this is why it's so useful to have that function stored in your calculator, because I just typed this in, integral 0 to 5 v of t dt. I hit enter, and it gave me exactly 35. So what that means is it's going backwards initially, but then it moves forwards, and it moves forwards far enough to cancel out the negative and even move it forward 35 units total to the right. Now that's for the position at t equals 5. So for that, the final position, if we look back at our formula, we need to add the initial position to the displacement. So that's going to be s of 0 plus the integral from 0 to 5 of v of t dt. S of 0 is 9, so it's 9 plus 35, which is 44. So we started at 9, we changed a total of 35 units to the right for a total of 44. Total distance traveled, so we're going to have to figure out this area as if it were positive plus this area to find out the total distance the particle went. But since it's a calculator problem, I'm just going to integrate from 0 to 5, absolute value v of t dt. So absolute value bars around the v of t. Again, if you have it defined, just throw those absolute bars around v of t. And I got that that value equals 42.5869. Okay. So we could do a little bit of math here and figure out that that actually means that the negative portion must be about 7.58. Then the positive portion is going to be enough to cancel out that, that 7.5 and get you to positive 35. Cool. Let's try one without a calculator. Oop. This one. This is a no calculator problem because they give us a graph that we can find areas of pretty easily. So here they tell us that at t equals 0, the particle's at 3. And they tell us the velocity is given by this graph right here, which we can find areas of pretty easily. I'm actually going to do that right now just because I'm probably going to need that. So here, this value down here, 1/2 base is going to be 1/2 times c, which is 1, times the height is -3. So that, if we were thinking about integral, would be -3. This guy would be 1/2 base times height. That's 3/2, or 1.5. This guy right here would be 3 times 1, so that's 3. This guy would be 2 times 1, which is 2. So they ask for the displacement from 0 to 5. That's just integral 0 to 5 v of t dt. So the negative will actually be negative this time. So we have -3 plus 1.5, that's our 3/2, plus 3, so those cancel out. And then plus 2, looks like 3.5 overall units. So it goes backwards for a while, but then that is canceled out eventually, and it ends up at positive 3.5 units. Final position now at t equals 5 will be s of 0 plus integral 0 to 5 of v of t dt. Well, we've got s of 0, they tell us it's 3. We add 3.5 to that and get 6.5. So that's where it's going to end up, because it started at 3, it initially was going backwards, and it goes forward far enough to go past its initial position and further on 6.5. Total distance, because we're doing it by hand, we're going to add up all those pieces. This is actually going to be positive 3 now, plus 1.5, plus 3, plus 2, 5, 8, 9.5 units. Not too bad at all. All right, let's try the next one. So here we have a table problem. They tell us a pump used to drain rainwater out of a storage tank. So that means that the water is actually leaving the tank. Let's read it all. Varying rates depending on how long it has been running. The rate in gallons per minute at which the pump can drain the water is given in 5-minute intervals in this table. The tank begins with 3,000 gallons. So we start with 3,000, and we are pumping water out of the tank. So we're trying to pump it down, probably eventually to 0. So this is the rate in gallons per minute, and they ask us what the integral of the rate means. Well, if we think about a tower of functions here, we'd have the amount of water, we'd have the rate that the water is being pumped, and then r prime of t would be like the acceleration sort of that the pump is moving. So if we integrate r, that's bringing us back down to the amount. So that's going to tell us the total amount of water pumped out of the tank between 0 and 40. So this is the amount pumped out from 0 to 40. Okay, so if we, too far. So if we figure out what that value is, that would actually tell us how much water has come out of the tank, subtract it from 3,000, and we would know how much is left. I think we're going to have to do that in letter D. So now they ask us to use trapezoids to estimate how much water has drained out of the tank in the 40-minute period. So you remember our trapezoids, we could do each one. So the first one would be 1/2 times 5 times 60 plus 68, right? Because we do the sum of it divided by 2, that's the average times the height. And then we're going to do that for each one of these. Or the shortcut would be pull out the 1/2 times 5, because we do have even intervals all the way through. They tell us it's at 5-minute intervals. So 1/2 times 5, and then we would do the first number, 60, and there'd be 2 68s, and there'd be 2 55s, because those are going to show up on each side of the trapezoid. And then the last one that you would have there would be 2 times 59, and then you would just have 165 on that last point. And I threw that into my calculator, and I got a final answer of 2,372.5. 2,372.5 gallons. So that's how much water was pumped out of the tank using trapezoids. It's not exact because we only have those 5-minute intervals, but it's going to be close. So now if you use that, what is the average rate at which water drains out? So the average rate would be the integral of the rate function divided by the length of time, which in this case is 40. So we've got the integral if you use trapezoids, so it's 2372.5 divided by 40. For that in the calculator, and I get 59.3125 gallons per minute. Now, if you look at our chart, that kind of makes sense, right? 59.3 is somewhere like within that range, and the average should be between the lowest and highest for sure. So now for how much water is in the tank at t equals 40, I would have to do a of 0, so the initial amount, and usually we would add the integral, but because we're pumping it out, I'm just going to say we're subtracting it, so 0 to 40 of r of t dt. So we must be using the trapezoids because we have no better way to do it. So a of 0 is 3,000 minus 2372.5. And that gives us 627.5 gallons. Sorry, I'm not showing you the calculator actual button presses here. I got my screen folded down, and also I'm just trying to keep the interest of time here so you guys make sure that you can see this by the end of the hour. If you have any questions about calculator, feel free to come in and ask. Okay, so now we got an AP problem. This is also a calculator OK problem. Otherwise, it would take forever. But what we're dealing with here is we have a rate at which people are entering an auditorium for a rock concert. So initially, it says that when the doors open, there is no one in the auditorium. So I'm going to say that A of 0 is 0. And the rate here is the rate that they're coming in. So like at time 0, 0 people per hour are entering. At time 1, I could plug 1 in here, 1380 minus 675. That would give me the number of people per hour that are entering. So it's constantly changing as t changes. So first thing they ask is how many people are in the auditorium when the concert begins? Well, I have a rate. I want the amount. So we think about amount, and the rate would be above, then r prime. So when the concert begins, so that'd be at t equals 2. So I need to know how many people came in between 0 and 2. So I do a of 0 plus the integral from 0 to 2 r of t dt. Well, a of 0 is 0, so that's nothing. And then I would just grab my calculator and do integral from 0 to 2. I would define this function in my calculator. I would just type this exact thing in, integral 0 to 2 r of t dt. And when I did that in my calculator, I got 980 people. So that's the total number of people that came in because I integrated the rate. Okay. Now they say they want us to find the time when the rate at which people enter the auditorium is at a maximum. So I want the maximum rate. Well, this is the function for the actual rate. So if I want to find when it's at maximum, I need to take the derivative and find out when it's 0. So we're going to find r prime of t, which we just move the 2 down to the front and the 3 down to the front. That gives me 2760t minus 2025t squared. And if we factor that, that's t times, in fact, we could pull out some numbers too probably, but I'm just going to do it this way for now. So we got 2760 minus 2025t. And we need to find the zeros. So it looks like 0 for sure is a candidate. And then I used the solve function on my calculator, or you could graph it and find the 0. T equals 1.36296 is also a 0 of that guy. That must be what makes this guy 0. So that must be, what, 2780 divided by 2025. So now we're going to test those. We should also test endpoints. So candidates. And you'll notice on my key I have online, I don't do this just because I ran out of room. But then we're going to find the amount at that, or sorry, the rate at that time to find our maximum. So our candidates are 0, 1.36296, and then 2. Endpoints and critical points. At 0, R of 0 is 0. We know that from here. If we plug in 0 here, we get 0. So that's probably not going to be a maximum. R of 1.36296. I got that, actually I don't have that value, but I'm going to use a sign analysis to be able to do that. You could plug that value in to find the rate, and showing that it's a maximum by candidates test would be enough. And then R of 2 you could find as well. But I actually made a number line. Here's 0, here's 1.362, and here is 2. And between 0 and 1.362, what's going to happen is this t is not big enough to make this negative. So you have a positive times a positive, that's a positive. And then after that value, this guy will be bigger, so it's going to be negative. So we show actually we come up initially, we hit a maximum, and then we come down. So both the endpoints are minimums. So the max happens at t equals 1.362 because r of t, r prime of t I should say, changes from positive to negative. There. Cool. Oh, jumped a little bit too quick in case you didn't see that. That's when our maximum happens. So now they bring in this weird formula. So they say the total wait time for all people in the auditorium is found by adding the time each person waits, starting at the time that person enters the auditorium and ending when the concert begins. So what they're saying is they're taking, like, the first person maybe enters the door at time 0. They're going to have to wait 2 hours. The next person maybe comes in 15 minutes later, so they're going to have to wait 1.75 hours. And then you add all of those wait times together for every single person. That is the function W. So you add all of the times together, and that gives you function W. They give us the derivative of W. They want W2 minus W1, which is going to represent the total number of hours people waited after time t equals 1. Well, that's just the antiderivative from 1 to 2 of w prime. And we have that function, so we can do it on our calculator. So we integrate 1 to 2, 2 minus t times r of t dt. Now, since I have r of t stored in my calculator, I'm just going to punch that exact thing in. When you hit enter, I got a value of 387.5 hours. So what that means is those 980 people we had from part A, all together, sorry, it's only the people that enter between 1 and 2, so that wouldn't even be correct. But the people that enter between hours 1 and 2, collectively they all wait at 387.5 hours. So now they ask, on average, how long does a person wait in the auditorium for the concert to begin? So that's going to be total time, which is our W function. So the total number of hours divided by the total number of people. Because that'll give us the number, because this is the total time everybody has to wait, divided by the number of people, that'll give the average time they have to wait. So that would be integral from 0 to 2 of our W function. And then we divide by the total number of people that enter between 0 and 2. So that'd be integral from 0 to 2 of r of t dt plus the initial amount. But we found that in the first part of the problem, it's 980. And then for the top, I'm just going to integrate from 0 to 2 on my calculator, 2 minus t times r of t dt, because that's how they define the function. And when all is said and done with that, I got 0.77551 hours. Now this is kind of weird to interpret, but what that means is that the average person had to wait about 45 minutes. So you might have had some that came before that, some that came after, like closer to the concert starting, but the average person waited about a little more than 45 minutes because it's about 0.77, which is close to 75 hours. And that's it. So that was really quick, but hopefully you were able to learn something here. And if you have any questions, obviously feel free to come in before or after school, and we can talk about it. Make sure you give your homework a shot. It's on your homework sheet and on the sideboard and also on Schoology. Love you guys. That's why I'm here. Have a great day. I will see you tomorrow.